The next phase we will discuss in our general chemistry module is the liquid phase, or solutions, in Lecture 9. We'll have to start off by talking about what the nature of solutions is. A solution is noted as a homogeneous mixture of two or more substances in a single phase. The solvent is what surrounds and dissolves the solute. For the purpose of the MCAT, you will generally see aqueous solutions as the most common, which is noted by the abbreviation AQ. Note that they have to be homogeneous, so if I look at any given solution, there has to be an even distribution of particles. So if I have a layer at the bottom, like so, this would not be considered homogeneous, therefore it wouldn't necessarily count as a solution until it's mixed. Here are some solubility rules regarding how these compounds are soluble in water. As you can note, there's a lot of exceptions to this. So in general, it's pretty difficult to keep a handle on this, but there are a couple really prevalent conditions that are generally not met with exception. All salts containing ammonium and alkali metals are usually water soluble, and that is usually without exception. And leads tend to not be soluble in general. You can take the time to memorize these, but it's probably going to be a little bit difficult considering that there are so many exceptions. Complex ions and coordination compounds are simply metallic ions that are bound to various neutral compounds and anions. One of the most common for these is water, or hydrations. This increases the solubility, and it's generally considered the opposite of the common ion effect, which we will go into later. Note that this coordination can be done through neutral compounds such as water or organics such as ethylene diamine, which is a very common one. In general, for the purpose of the MCAT, you will go into this discussion, but you need to know what it does to the metal, and you also need to know what kind of shapes these compounds will generally form. More often than not, these are going to be octahedral. The common ion effect. I'm sure you've heard of this before in your chemistry classes, but the common ion effect quite simply states that adding an ion will reduce the solubility of a compound with the same ion in it. So, what do I mean by that? Well, if I were to look at something simple, for example, sodium chloride dissolution. So if I had a sodium chloride dissolution, so if I went from a solid, put it into an aqueous mixture, and got some sort of aqueous blend of sodium and chloride ions, if I were to add potassium chloride, that's going to increase the chlorine concentration here, therefore decreasing the solubility. The same would apply for sodium. So if I added something like sodium fluoride, the sodium in this case is going to do very much the same thing. Think about your Le Chatelier's principle. You're effectively increasing the amount of a specific product, therefore forcing the reaction back. In the purpose of solubility, this is going to decrease the likelihood of solution. There are different ways to quantify concentration. Let's go into those in the next portion. Here are three common ways that they are represented. There is percent composition by mass, which is simply done by mass of solute to mass of solvent as a percentage. A mole fraction, which is simply stated as the moles of the desired compound over the total. And molarity, which you'll always see, because this is moles per liter. Molality is less common. Instead of using liters, it uses kilograms of solvent. This conversion can be done fairly consistently, considering that 1 gram is more or less 1 milliliter. So it's more or less 1 milliliter. So when you're doing your calculations and you have to go from grams to liters, this is the conversion you should keep in mind. Normality is a little bit more complicated because it varies depending on the equivalent of interest. Usually speaking, you're going to see normality in acids and bases, which is actually incidentally our next lecture. Normality can quantify anything from hydrogens, hydroxides, or electrons. So if I were to go into this, for example, if I were to look at an acid, let's say HCl, this would have one normal H. Whereas if I were to look at H2SO4, this would be considered two normals. So I have one normal and two normals. And obviously, this can continue on indefinitely. So basically, you need to look at what your equivalent of interest is when you're doing your calculation. Especially with acids and bases, this is going to be important. A dilution is quite simply stating that the molarity times the volume has to be the same for the initial situation and the final. So we've covered our measures of concentration. Let's go into solution equilibria. As you can see, equilibria has come up once again because it's a very important principle in chemistry as a whole. We'll have to start with the solubility product constant, or simply stated as KSP. What you're going to notice is that this looks very similar to KEQ. It is a measure of KEQ, or equilibrium, but it's tailored specifically for solution equilibria. This revolves around the saturation point, which simply states that the solution concentration is at the maximum for a given temperature and pressure. And the equation for KSP is listed below. What you're going to note is that it's identical to KEQ, except that you do not include the reactant, or the other side. Why? Because it's a pure solid. The formation constant Kf is the equilibrium constant for complex formation. This is to indicate the saturation point, which the definition is listed above. Although KSP is very important, we do have to look at ion product when we're looking at solution. Ion product, quite simply, is an analog for the reaction quotient, or Q, and its relationship to KEQ. If the ion product is less than KSP, that means that the solution is unsaturated, meaning that you can put more solute into it. If the ion product equals KSP, the solution is considered saturated, or at equilibrium, or at capacity of solute. And if the ion product is greater than KSP, the solution is considered supersaturated, meaning that there's more solute than the solvent can handle. A very good example of this kind of solution equilibrium is if we were to look at sweet tea. I don't know if you've ever had sweet tea before, but it has a very, very high sugar concentration. The way they get this sugar concentration so high is by boiling the tea while they're putting the sugar into it. By heating it up, you're allowing more solute to go into solution. Therefore, you can add more sugar than what you normally could do at room temperature or colder. The same would apply as if I were to cool it. The thing about sweet tea is, if you let it sit for too long in the refrigerator, the sugar is going to come out of solution. Why? Because it gets colder, therefore decreasing the saturation. This applies for most things. You're going to notice that if you boil something or heat something up, you're going to have an easier time putting things into solution. So, for example, putting sugar in your morning coffee, or putting something like honey into your tea. The hotter this liquid is, the easier it is to dissolve things into it. And obviously the opposite is true. Just remember that ion product and the KSP are similarly related as Q and KEQ. Finally, we'll finish up the lecture talking about colligative properties. Colligative properties are noted as properties that are physical, that are dependent solely on the concentration of dissolved particles. The chemical identity is not important of these dissolved particles, however. The only thing that matters is how many there are. Properties include things like vapor pressure depression, boiling point elevation, freezing point, and osmotic pressure, which is listed here in this diagram. Speaking of vapor pressure depression, we need to talk about Raoult's law, which simply states that the presence of other solutes will decrease the evaporation rate of a solvent without affecting the condensation rate. It states that as vapor pressure decreases, the temperature of the boiling point increases, and the expression mathematically is listed below. P of A is the vapor pressure of solvent A, and the solutes present when solutes are present. XA is the mole fraction of the solvent A, and P naught A is the vapor pressure of solvent A in pure state. Other equations include the freezing point and boiling point, which is noted below. What you'll note is that freezing and boiling point equations are identical, except for some constants. Delta T is quite simply the increase in boiling point, or freezing point, I being the Van't Hoff factor, which is identical for the two cases, and Kb being the proportionality constant characteristic of a particular solvent. Note that for boiling and freezing, this is going to be solution or element or molecule specific. Lastly, M is the molality of solution. Take note that is molality. It's not based on molarity, so make sure you're mindful of that. Osmotic pressure depends on the molality of solution as well, and it's given by pi equals I mRT, whereas pi is the osmotic pressure, I being the Van't Hoff factor again, M being the molarity of the solution, and R being the ideal gas constant. Lastly, T is the temperature. Osmotic pressure is the pressure generated by the flow of water. So if something has a high osmotic pressure, it's going to have a very, very intense sucking pressure generated by solutions in which water is drawn into it. Take note that the Van't Hoff factor will be provided to you come test day. We'll finish our discussion of solutions at that point. In the next lecture, we're going to go into acids and bases and how it pertains to our daily life, and more particularly for the MCAT. We'll see you then.